Okay, great. Thanks so much. So my name's Siyang, or I also go by Sean. I'm a postdoctoral fellow at UC Berkeley, where I'm supported by the Princeton Foundation. And I first, of course, like to thank the organizers for the opportunity to speak on the TRGB and the JAGB. And I was planning to be in Florence in person, but I had a family emergency come up, so I wasn't able to make it. So thanks again to the organizers for being able to reschedule my talk, and I believe Martin too, who had to switch with me. So I really appreciate it. So today I'll be giving a review talk on the tip of the red giant branch, or the TRGB, and the J region asymptotic giant branch, or the JGB, using those as standardizable candles to measure distances to galaxies, as well as calibrate brighter candles, such as type 1a supernovae, to measure the Hubble constant. And so I'll be giving a brief overview of their current status, systematics, and their role in measuring the Hubble constant. Now, in this talk, I'll begin with a bit of a background. So I know there were excellent talks yesterday on the Hubble tension. So I won't be, of course, reviewing the Hubble tension, but I will spend a little time reviewing what a distance ladder is, how we build a distance ladder, and how that relates to the candles that I'll be talking about. I want to motivate why we still care about the TRGB and JGB. Of course, we that's one of many other standard candles. And then I'll split the main part of my talk roughly 50-50 between these two candles, TRGB and JGB, and wrap up with some conclusions. Now, the distance ladder is based on a very simple relation, a little bit of algebra as shown here. And so this is kind of the cornerstone of our work. So we have little m minus big M minus a equals mu, the distance to a galaxy. Our little m is our apparent magnitude. We observe our candles, the apparent magnitude of our candles using telescopes like the Hubble Space Telescope, the James Webb Space Telescope. Capital M is the intrinsic brightness of our candle, and that's what we take advantage of. That's something that doesn't vary too much galaxy to galaxy. We do have to correct for attenuation of light due to dust extinction in our line of dust in our line of sight. And really, those three quantities give us mu, the distance. And so conceptually, building this distance ladder is very, very straightforward and simple. So in practice, when we construct the distance ladder, our first step is what we want to calibrate the intrinsic brightness of our candle, such as Cepheids or TRGB. Essentially, this means we want to first find what capital M is for our candle. Now, we typically do this with nearby galaxies such as NGC 4258, where they're nearby and we already have a geometric distance directly readily available. In this case, for NGC 4258, a water maser system rotating around the central black hole. Now, these systems where we have a geometric measurement are very rare and very few, so they're kind of special. We don't have a geometric distance to all galaxies or most galaxies that we work with. So I reproduced the little simple relation down here where I took away a just for simplicity. Again, that's little m minus big M equals mu. Our goal here in our calibration step is to solve for capital M for our standard candle. Now we can measure little m, the apparent magnitude for our candle with our telescopes, HST, JWST. We do know the distance to this galaxy geometrically for these nearby systems, that's mu. And with these two knowns, we then solve for the capital M, the intrinsic brightness of our candle. We can then take this information to measure distances to even further galaxies where we no longer have a geometric distance available, such as NGC 5584. Now, we take advantage of the fact that for candles, again, capital M doesn't vary too much galaxy to galaxy. We're trying to solve for mu, the distance to this galaxy. We know capital M for our candle. That's based on our calibration set from NGC 4258, for instance. We can then measure little m, the apparent magnitude of our candle in our distant galaxy with HST or JWST. With those two knowns, we can then solve for the distance, mu, to NGC 5584. Now we can then take this one step further and then kind of repeat this process to calibrate an even brighter standard candle such as type 1a supernovae. In this case, we take this distance to, for instance, NGC 5584 using Cepheid's TRGB JAGB, calibrate the intrinsic brightness of type 1a supernovae, and then use that information to measure distances to even further type 1a supernovae further into the Hubble flow. To kind of summarize that, we first use geometric distances to calibrate the intrinsic brightness of our candle. We use that calibration to measure distances to further galaxies where we no longer have a geometric distance, and then we repeat that process. We then, instead of using a geometric distance, use that derived distance using TRGB Cepheid's JGB to calibrate the intrinsic brightness of our type 1a supernovae. Repeat that process to measure further into the Hubble flow. So I would say that at the moment, the 4 anchor Cepheid Type 1a supernova currently is the most mature ladder, distance ladder, yields the highest precision H naught. By 4 anchor, I mean that we have 4 galaxies that we can use to calibrate the intrinsic brightnesses of these Cepheids. And the motivation for a lot of these TRGB and JGB works, testing their systematics and also measuring the Hubble constant, is to also really test the robustness of this ladder in particular as well. And so a lot of the overarching objectives of a lot of TRGB and JHB work is really to develop ways to measure distance to the galaxies and the Hubble constant independently from the Cepheid distance ladder to test its robustness and also test whether systematics plays a large role in the Hubble tension. So the idea here that, again, if we have a set of galaxies and we can measure distances with Cepheids, for instance, same set of galaxies, we measure distances with an independent method like TRGB or JGB, and they agree very well that would be very good evidence in support of the robustness for those measurements. And so we have the TRGB that we can work with, and there's also a recent revival of a relatively new standard candle called the JGB that uses carbon stars as standard candles. And of course, I'll be talking about these for the main portion of my talk. So in the first parts, I wanted to first briefly cover why can we use the TRGB as a standard candle and what physics motivates it. So the TRGB originates from very low mass stars, about less than about 2 solar masses, and these low mass stars really allow for this electron degenerate helium core to form. So as hydrogen burns, it does deposit helium into the core. This causes a hydrogen burning shell around this helium core, but because of the mass, the helium burning cannot trigger yet. And so as this helium core increases, it does grow in mass until it reaches about half a solar mass. At that point, a temperature reaches the critical temperature, about 10 to the 8 kelvins, and that is when helium burning is triggered, and that leads to an event called a helium flash. So there's a runaway nuclear effect, and essentially, the helium flash lifts the degeneracy of that core. The star is allowed to expand, and the star suddenly decreases in brightness. And so the idea here is that as it increases in brightness, as the hydrogen burns and burns, these red giant, these low mass stars become brighter and brighter. It hits this critical mass, leads to this critical temperature, reaches a maximum brightness, and then it falls off and becomes very fainter. And then that's what causes kind of this feature called the tip of the red giant branch. So we can see this kind of in this diagram to the right here. So again, as I mentioned, in this red giant branch, these low mass stars, as it evolves, it gets brighter, brighter, brighter. It reaches the helium flash, and then as it gets expands, it gets fainter, and then transitions onto what we call the horizontal branch. And it's this feature where you might go up, brighter, 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 get fainter, that causes this kind of tip, this maximum brightness caused by these stars. And the idea here is that because this helium flash is triggered at roughly, very consistent solar core mass as well as the temperature, the mass range, the core mass range for this event is relatively well constrained, and that also translates to a relatively well constrained maximum luminosity that then sets the TRGB. Now, in theory, does predict that the magnitude of this maximum brightness is not too sensitive with age. There is a small dependency on metallicity, which then translates to color, and I'll talk about that in a little bit, but that's something that you can calibrate for and correct for. And so essentially, the TRGB has an intrinsic brightness, or a capital M, that's roughly around -4 magnitudes, and the I band, which is relatively pretty bright, allows us to reach from 20 to 30 megaparsecs, in a very, standardizable, but also very small scatter in this TRGB. Now, I did mention that the TRGB does have a little dependence on metallicity, which can also be empirically observed with the color of these stars. And so I just wanted to touch upon that by a little bit. So the TRGB is most commonly measured in the I band, and that's because that is the band where this metallicity or color dependence is least sensitive. Or HSD, for instance, the Hubble Space Telescope, that corresponds to roughly an F814W filter. For the James Webb Space Telescope, that's the F090W filter. And essentially, many people choose that filter because as you go to redder colors or redder filters, this metallicity dependence becomes steeper. What I'm showing here on the right is a plot from the Zhang and Li 2017 paper who had calibrated the color relation for the TRGB here in the F814W band. You can see that on the x-axis is the color. So to the right, we go redder, to the left, we go bluer. Y-axis is just the TRGB magnitude. And as you go to redder wavelengths, or in redder colors for these stars, the TRGB does start to drop off and become fainter. Now, the Jang paper does, and other papers such as Brizzi and Newman also do see that in a certain color range in the I band, you can approximate a bluer region as relatively flat and insensitive. So that's the reason why the I band is used most commonly here. If you go to redder filters, like with JLOST, F115W, for instance, F277W, this color dependence does become steeper. And the same thing for bluer wavelength. So this I band is kind of the sweet spot to kind of avoid a steeper color relation as shown here. Now, in principle, when we have tried to measure the TRGB, we do target the halo fields of these galaxies. And so the very outskirts of these galaxies, here's a nice image from Deep and Non's paper back in 2024. And we want to target the halos of these galaxies because that's where the stars are relatively sparse, so there's low crowding. That's compared to, for instance, Cepheids, where you have to observe them in very crowded environments. And that does cause what we call a crowding bias. So there's a brightward bias due to contamination of light due to nearby stars in your photometric process. If it's too crowded, that's something that's correctable. But of course, if we can avoid it, we'd avoid it. This region also does minimize effects of internal extinction that can be a very small effects. But also because these halos contain these very old stars. So the stars that we want to use for the TRGB, as you get closer to the disk, of course, you get these younger stars that are not used for the TRGB. And of course, we want to avoid contamination as much as possible. Now, ideally, when you measure the TRGB, you have these red giant stars. And if you plot a histogram of the brightnesses of these stars, you get what we call this luminosity function right here. And so you can imagine kind of you see this luminosity function, which is again just the histogram of the brightnesses of these stars. If you start from the right here, and you start with your red giant, as the red giant evolves, as I mentioned before, it gets brighter and brighter. You can imagine that going from the rightward direction of this plot to the leftward. And then once it hits its, maximum luminosity, when the helium flash is triggered, it kind of stops at this TRGB magnitude. And then it'll become much fainter, transition onto the horizontal branch, and you won't see it on this luminosity function. So what this causes in this luminosity function is this very steep drop-off, in the number of stars. You do see, of course, there's this leftward region here. Those comprised mostly of asymptotic giant branch stars. So more evolved stars that happen to have, similar colors, but also are much brighter than these red giant branches. Ideally, for a very well, high signal to noise data, you will see a very sharp drop off. You can approximate that with maybe a broken power law model, as shown here. Now, the problem is that with data, of course, data is very noisy. And so we don't in practice see a very sharp cutoff. So what I've shown here on the right is it's a color magnitude diagram that's kind of rotated on its side. What I really want to show here is this luminosity function. So it's shown here in purple in Dan Skolnick's paper. So of course there's noise. So when you make a histogram, there's Poisson noise. There's photometric uncertainties that add errors to your magnitudes. There's some contamination from younger stars or AGB stars. And of course, if you get too faint, there's also incompleteness that you might have to worry about. So what that causes in practice is that instead of this very, very drop cutoff, you do see this kind of sloped cutoff, if you see kind of see here. So if you the measured TRGB in this diagram is marked by this dashed blue line. And you can see here that there's a purple line shows kind of this luminosity function. And even at the TRGB, the luminosity function is a little kind of sloped. It's not very sharp. And that's where, there's some complications that arise due to your measurement process. What parameters you choose in your measurement process, how you smooth the luminosity function. I'll talk about that later on. And that can also cause variations in TRGB measurements that will also propagate into the Hubble constant. And so I think that's something I want to frame first before I start talking about and reviewing other papers. So again, the goal here, really, the goal of measuring the TRGB is to identify this drop off, this edge that we call this discontinuity. Now we can do this a few different ways. So one way is what we call using a Hubble filter. I'll talk about that in a little bit. You can also fit a model, a broken power law model, to this discontinuity or this luminosity function. Either way, whatever method you use, you're essentially just trying to identify this location where the first derivative of the luminosity function is at its maximum, this drop off. So one commonly used approach to measuring the TRGB is what we call using edge detection. We essentially want to measure the first derivative of this luminosity function, find the maximum value of the first derivative, and use that as the TRGB. But as I mentioned before, the luminosity function can be very kind of noisy. There's Poisson noise. Your bins will fluctuate. And so what many people do first is they apply smoothing. This is pioneered by the CCHP team, applying this glow as smoothing. In a nutshell, what this does is for every bin in your luminosity function, you do fit a linear line to the points around the luminosity function, but the bins around that luminosity function are weighted by Gaussian. And you can control the width of that Gaussian used for the weights using what we call a smoothing parameter. And I'll talk about that, how that can affect your TRGB measurements later. But essentially you do that for all the bins, and that kind of builds a smooth luminosity function where you can then make your TRGB measurement on. So here's a kind of comparison of what happens when you smooth a TRGB luminosity function. So again, we have our histogram, our broken power law histogram, sharp drop off here. This is using simulated data points. When we use a low smoothing, so if we turn down the smoothing for this measurement process, you can preserve this discontinuity, but you do see that there can be some, bumps and wiggles in this smooth luminosity function. As you crank it up, though, you can smooth out those bumps and wiggles, but you do start to kind of smear out this discontinuity. And I think that that's natural because you're applying smoothing to a non-smooth luminosity function. What that can happen, though, is then that can also start to bias your measurements. And so that's a measurement choice that people have to make when measuring the TRGB. And ultimately, that's a measurement choice that kind of will affect your measurements, will then propagate into your distance measurements, and then ultimately into your Hubble constant measurement. So I think I wanted to kind of frame this as I'm explaining how to measure the TRGB, so you have an idea of how that plays a role in later H0 measurements that I'll be presenting. So I wanted to show really quick kind of what effect the smoothing has on these measurements. So again, we have our luminosity function shown here on this right here on the right subplots. We can apply different smoothing values to this luminosity function. So here in the blue, we're showing a low smoothing. So when you have those Gaussian weighted, the width of that is relatively narrow. we have a larger smoothing value applied to this luminosity function that's shown here in the red. If we apply the same measurement algorithm, you do see that the smooth value or the smooth luminosity functions look different. That's shown here in the kind of the dashed lines above the black histogram. You can see too that this creates kind of this area shown here in red. So as you increase the smoothing, there's this additional kind of stars that are pushed down to this red area. And again, that also does change the value of your TRGB. So that's what we show here with the horizontal lines, red and blue. So after we smooth the luminosity function, what we do is then we apply an edge detection. So essentially, we want to find the first derivative of the luminosity function. Now, of course, we don't know, the equation or, of the luminosity function. So what we do is we apply what we call a Sobel filter, a kernel, to apply across the Sobel filter to kind of measure the first derivative from each of the bins. And so this was the concept that was adopted from computer vision. And essentially what you do is you multiply the bins by -1, 0, or +1, add them together, and essentially it's just a way to kind of measure the derivative of the luminosity function in a binned approach. And so typically that's what we do. That Sobel filter then produces what we call a Sobel response, as shown here on the top panel of this plot. Essentially gives us again the first derivative. We then take the maximum the location of the maximum Sobel response as the location of our TRGB, and that usually matches pretty well with our simulated data. Now, there's another approach that we can take, and we can also fit a model. So I mentioned that this luminosity function can be kind of, described as a broken power law model. There are also, papers in the literature that do take this approach. Essentially, you have several parameters that you fit, so you can use linear least squares fitting or maximum likelihood fitting to kind of just fit the bins or fit this luminosity function to have a discontinuity here between two power law slopes. And so that's a very quick rundown of kind of two major ways to measure the TRGB. And so in this third part, I did want to spend a little more time to kind of cover some major programs that measure the TRGB and the Hubble constant to kind of give a landscape of the TRGB in the context of the Hubble tension. So I wanted to begin with a major group, the Carnegie Chicago Hubble Program, CCHP. Many of you guys must probably heard of this group. That was really has been investing a lot of time and effort over the past, several years to measure the TRGB using Hubble Space Telescope, James Webb Space Telescope data, measure the TRGB in many galaxies, to calibrate Type 1a supernovae, to measure the Hubble constant independently of Cepheids, again, to really probe the Hubble tension and to test whether the Hubble tension is primarily due to systematics or unresolved systematics in the Cepheid and Type 1a supernova distance ladder. So here's just a snapshot, one of their major papers back in 2019 that had really launched their program. So when the CCHP adopts the edge detection or Sobel filter approach that I just described, so again, they smooth the luminosity function with GLOWES, and that's actually something that was pioneered by them. Then apply a Sobel filter, or kind of a way to measure the first derivative of the luminosity function to measure the TRGB. They do perform, so just as a note, they do perform photometry in their HSD data with a custom pipeline using a software called DAO FOTS. And they do adopt the Carnegie Supernova program, Supernova Photometry, which is a subset of another major supernova compilation, for instance, Pantheon Plus. There will be differences that can be traced back to this difference in supernovae selection, and I'll talk about that a little bit later on. So on the right here, I'm just showing an image from their paper showing the kind of the footprints of their observation. So as I mentioned, the TRGB is primarily measured in the halos of galaxies. And so here in the hatched region, that shows kind of the regions that they used for their measurements. And again, a lot of these observations are primarily kind of designed and focused on measuring the TRGB in their program. So they did initially use HST, but very recently they also did take advantage and had a successful JWST program as well. So in this program, they observed 10 galaxies hosting 11 Type 1a supernovae, and they using this JWST measurements, the TRGB, they do find an H naught of roughly 68.8. Here on the right-hand side is kind of showing their a figure from their paper. I will note that this value did kind of fluctuate. So if you look in the archive, there are multiple versions to their Hubble constant. So it just an FYI. So it does kind of fluctuate version to version. But their program did seek to measure the TRG with JWST. They also made a JAGB measurement too, which I'll talk about that later. Also, Cepheids with their JWST program. Combined, they get a Hubble constant of roughly 70. And they and that's just for a little context. One of the major groups, the results for one of the major groups. Here's just the compilation of their recent results. So again, Friedman HST results hover about 69.8. Their first result from 2019, they updated their result with the Hubble Space Telescope data by adding more calibrators in their 2021 paper. And of course, they did come out with a recent result with James Webb Space Telescope data. That's covered by the Friedman paper, as it also Taylor Hoyt's paper, and that gives also a very low H naught as well. So another major group that uses the TRGB and measures TRGB distances is the Extragalactic Distance Database Team, or EDD. And they have a very well-organized and public database containing the photometry and data that they use in TRGB measurements in many, many galaxies, not limited to these Type 1a supernovae hosts. There's hundreds of galaxies they measure distances to. The goal of what they did when they were measuring the Hubble constant was essentially to reanalyze a lot of the archival HST TRGB data to calibrate Type 1a supernovae hosts and then see how that really compares with the CCHB results. Now, the EDD team does have their own TRG measurement pipeline that differs a little from the CCHB team. So, for instance, they use a different photometry suite, Dulphotes. They use a different measurement approach to the model fit approach that I mentioned before. That's in contrast to the Sobel filter approach. And essentially, what they did was kind of test, if you use a very similar underlying data sets, apply different measurement and selection approaches to that data, measure the TRGB, how does that differ from other H0 measurements, such as from CCHB. Now, along the way, one of their main findings when kind of reanalyzing this data was that not all the data is actually really yields a robust TRGB. And I kind of wanted to emphasize this. So on the right here, one plot from Deep and Non's paper in 2021. These shows these color magnitude diagrams. So the brightnesses of these stars on the y-axis and the I band, so the HSD I band, F814W, as a function of the color. So again, right is red, left is blue. Now on the left-hand side, they're showing kind of a, really pretty robust TRGB measurement in a color magnitude diagram for NGC 1316. You can kind of visualize this TRGB drop-off or this discontinuity pretty well visually by eye. You can see this as you go from the bottom to top direction. You see a very sharp drop off in the number of stars. But for 4 galaxies that were used in the CCHB data set that they noted, if you look at their color magnitude diagram, the drop off is not very apparent. It's very difficult to locate it by eye. Very difficult to even, if you apply a model fit, to really identify where that discontinuity is. And so one major finding that they had in their Hubble constant measurement was that essentially they could not measure a robust TRGB from these 4 galaxies from the data that was used by CCHB to measure the TRGB with. And so as a result, they concluded that they could not recover TRGB and had to exclude that data from their H0 measurement. So their result ended up being around 71.5, plus or minus zero point 0.1, 0.8 kilometers per second per megaparsec. This does differ from the HST value, H naught value from CCHP. There are several differences that are traceable and that they note in their paper. So on average, when they use their own pipeline, the TRGB distances do differ by about 3/100ths of the magnitude. Some other differences that does cause a little difference in this H naught value is that EDD does apply a color correction. So I mentioned before that the TRGB does have a dependence on metallicity, which is traced by color. That's something that's not applied in the CCHP analysis, although that has a little effect. As I mentioned before, there's four galaxies that were irrecoverable in terms of measuring the TRGB and the EDD reduction. That also does shift H naught as well. And again, they include EDD did include the full Type 1a supernova data set that was available at the time, whereas in CCHP, they did exclude some Type 1a supernovae. So I think on the right here is a plot from that same paper where they're showing a comparison between their results shown here in brown, which is a little higher than what the CCHP team found and is a little more consistent with the Cepheid-based H naught. And so I think it's important to kind of note here is that there are many different ways you can measure the TRGB, different pipeline, different, measurement approaches. And TRGB H naughts, while this, for instance, in one major group, CCHB does find a lower H naught, there are also other groups that also find a little higher H naughts that are more consistent with the local values, for instance, of H naught, for instance, from Cepheids. Now, there are also other independent groups who measure TRGB-based H naughts, independent from CCHB and EDD, for instance. And so there's another major effort that uses TRGB and also surface brightness fluctuations to measure the Hubble constant. The idea here is to make this distance ladder completely independent from Cepheids and Type 1a supernovae. So in this case, the TRGB kind of replaces Cepheids, and these SBF surface brightness fluctuations then can replace the Type 1a supernova using that distance ladder. Now, the surface brightness fluctuations, or SBF, is kind of based on this idea is that as you go further, as your galaxy is further, the observed surface brightness or kind of the smoothness of your image of your galaxy does get smoother and smoother because, of course, as you go further, everything kind of blurs together, and using that as a proxy of distance. And so there have been papers published, for instance, by Jensen et al., Blakeslee et al., that have kind of constructed this TRGB and SBF-based distance ladder to be independent of the Cepheid-based distance ladder and Type 1a supernovae-based distance ladder. And they do find with this TRGB calibration a little higher H naught, so 73.8 from Jensen 2025. In an older version of this approach from the Blakeslee paper, 73.3 as well, which are a lot closer to the Cepheid value compared to the early universe value of H naught. Now, there's another effort that was kind of done recently called the team was called CATS, or the Comparative Analysis of TRGBs. And this group that I was also a part of kind of started this effort to measure the TRGB based H naughts, but first addressing this problem that we kind of observed in many TRGB measurements. And that we did see that there were variations in TRGB measurements when you look at different fields, for instance, in the same galaxy, and also variations that arise due to different measurement choices. So as I mentioned before, for instance, when you apply smoothing, you can apply different smoothing values, for instance, that can shift the value of the TRGB by certain amounts. And of course, that can propagate to the Hubble constant measurement. So to approach this, the CATS team adopted a twofold approach. And so the first was to develop an unsupervised TRGB measurement algorithm that you can apply consistently across all the measurements to avoid subjective biases. So again, you don't have to decide which smoothing to use, for instance. And then again, to apply an additional standardization to improve consistency along the distance ladder. So, as we mentioned, we do observe these variations in the TRGB from field to field, for instance, suggesting that there could be additional standardization that's not baked into existing TRGB measurements. And so we thought that by introducing a different metric, what we call the contrast ratio, and I'll talk about that in a little bit, that can also help make our Hubble constant measurements more consistent. So on the right here, I'm showing kind of a plots depicting all the TRGB halo fields that have been observed in NGC 4258, our calibrator galaxy. So what's really great about this data set is that we have roughly around 10 fields to work with, and we can measure the TRGB in each of these fields using the same exact measurements algorithm. And the idea here is that ideally for a standardized candle, you would expect that the magnitude or the brightness of your candle shouldn't really differ significantly depending on which field you look at. Because of course the distance in the galaxy is fixed, right? But when we did this to all these fields, measure the TRGB in all these fields, we do find that there's quite a bit of variation. So these TRGBs vary by almost 3/10 of a magnitude if we apply the same exact measurement choices. And of course, that's an issue because we don't know, which TRGB then value do you use to calibrate your type 1a supernovae? Do you use the one that's brighter or do you use the one that's fainter? That can be an issue. So along the way, we found that this variation in the TRGB measurements did have a relationship with what we call the contrast ratio. So the contrast ratio is defined as the number of stars that are half a magnitude fainter than the measured TRGB over divided by the number of stars that are brighter than the measured TRGB. So essentially this measures how sharp your discontinuity is. Now, in Jaxi Wu's paper back in 2022, when he kind of investigated this effect in a lot of TRGB data from our underlying photometry from the ghosts field, he did find kind of a relationship between this measured TRGB and this contrast ratio. And the idea here is that if we found a roughly linear relation, and then if we can then measure the contrast ratio for this underlying data sets, we can then correct for this variation in the TRGB and to make our H0 measurements more consistent. So we first applied this to NGC 4258, for instance. So that's what we show here on the top here in this top panel. Again, on the y-axis is the measured TRGB in the I band as a function of, again, the contrast ratio, the number of stars half a magnitude fainter over the number of stars half a magnitude brighter. We did this in NGC 4058 in a paper that I published. We compared that to the result that Jaxi Wu found in this ghosts fields data set. We found very good agreement. We came up with a calibration. Essentially, we can calibrate the TRGB capital M, the intrinsic luminosity based on some fiducial magnitude, in this case, negative 4.03. But this is a function of this contrast ratio. So contrast ratio 4, we have this fiducial TRGB. But if you have a galaxy that yields underlying data, where you have a TRGB measurement with a contrast ratio R, maybe 5 or 3, you can then correct for that using this relation here. And the idea there is to be correct for this in your calibration galaxy, such as NGC 4258. Do the same thing in your type 1a supernovae hosts. You can then make your calibrations a lot more consistent and then be a lot more consistent when you measure the Hubble constant with this data. So in the CATS efforts, we did publish our H0 results in Dan Skolnick's paper in 2023. We did find an H0 of roughly 73.2. Here, all the data that's used and all the algorithms for this are public. So we use the EDD photometry, which are public from the website that I mentioned before. We also have a GitHub repository where we release all the algorithms to be publicly available. That's described in the Wu 2022 paper. And so what we did find is that when we compare the H0 results to other H0 measurements from CCHP, for instance, or the EDD results, a lot of the differences are traceable. So for instance, applying this TRGB contrast ratio relation, does change the Hubble constant by about 1.4 compared to CCHP, about zero point 0.3 compared to EDD. There's also traceable things, for instance, applying peculiar flow corrections, which would shift. So we do that in the CATS results. That's not done in the CCHP team results. That shifts things by about zero point 0.4. ADD did incorporate those corrections as well. There's also, other effects here that are listed in this table. So the bottom line here is again, the CATS team, or what we did, is another independent reduction of TRGB photometry and data to find another H naught value, and any differences between other, measurements in the literature are also fully traceable. So this is no mystery why different groups get different TRGB values. I did also wanted to touch upon some other and acknowledge some other efforts that are also independent from these teams that I just talked about. So Suhail, back in 2022, did also measure the Hubble constant using supernovae from the ZTF, Sochi's transient facility. In his study, he did measure the Hubble constant using a single Type 1a supernovae calibrator, so NGC 7814, measured a TRGB distance to that galaxy, then used that TRGB distance to calibrate the intrinsic luminosity of Type 1a supernovae using supernova 2021 RHU. In that study, he did find a much higher Hubble constant, 76, almost 77, with a relatively large uncertainty. And again, the uncertainty is very large. This not very tight constraints because they were only using a single Type 1a supernovae as calibrator in a single galaxy. There's certainly a lot of potential for expanding this if they so choose. But again, I think the importance here is to really kind of emphasize that there are also other efforts, other teams using different data sets, different measurement methods to measure the Hubble constant in the literature. Now, I did also want to acknowledge like another H-naught measurement, TRGB base, also published by Suhail back in 2023. Here he used a combination of optical and near-infrared Type 1a supernovae. In this case, he looked at using both Cepheids and TRGB to calibrate the Type 1a supernovae. For TRGB, the results around 70.92 or around 71 kilometers per second per megaparsec. And so, again, that's another example of another independent team, another independent method efforts using TRGB to measure the Hubble constant. Now, of course, there's another great opportunity to take advantage of the James Webb Space Telescope, so launch of the JWST. Now, I wanted to talk about some recent efforts by the SHOES team to also use the TRGB JWST observations of the TRGB to also measure the Hubble constant. And so the launch of JWST has really provided an excellent opportunity to also do these cross-check with Cepheids, of HSD Cepheid distances. So we can leverage the independence of the instrument, so JWST versus HSD, as well as the independence of the method, so Cepheids versus TRGB. So when the SHOES team looked at TRGB with the James Webb Space Telescope, what we found was there's definitely a very significant increase in the resolution and of the CMDs. So the TRGB discontinuity is much cleaner. That's shown here on the right here. Here's an example of the CMD for NGC 1559. And what we did in the SHOES group was to then adopt the CATS algorithms to measure the TRGB using the JWST data to kind of then see what TRGB distances we get, compare them with Cepheids, and ultimately what H-naught value we get. So we measure distances to this initial data sets. We do find very excellent agreement with the HSD Cepheid distances to the same set of galaxies. So in the plot to the left here on the y-axis, we're showing distances to these set of galaxies using JWST TRGB. On the x-axis, we're showing the Cepheid HSD distances to those same galaxies. And if we simply take a weighted mean of the difference between these distances, difference about zero point zero 0.01 magnitude, so very excellent agreement. So with this data set, there's no evidence of a significant systematic in the HSD Cepheids that would be able to resolve the Hubble tension. Now, in this iteration, we did not measure the Hubble constant just yet. We focused on just the differences between the HSD Cepheids and the JWST TRGB measurements. But of course, one of the major limitations of this study is the sample size. We're only working with a limited number of galaxies. So we did do another iteration of this study where we tried to expand the TRGB sample size and expand the TRGB measurements that we use for an actual Hubble constant measurement. So in this new iteration, we did measure the TRGB in 5 galaxies using data in the HST archive that weren't published before. So on the right here, we're showing color magnitude diagrams and luminosity functions for these galaxies. And then the goal here was to combine these new measurements with all the TRGB measurements in the literature to really maximize the statistical leverage we have on comparing the TRGB with Cepheids as well as measuring the Hubble constants and comparing that with the Cepheid-based Hubble constant as well. So what I'm showing here on the left is a plots from the paper. You see a lot of orange dots here. And so what each of these orange dots shows is an value of the Hubble constant if you had used a single type 1a supernovae calibrated with TRGB to measure the Hubble constant. And you can see that there is quite a bit of variation. So for instance, the Hubble H naught can measure between 87 to 56. That's entirely expected. That's dominated by the intrinsic variation of the type 1a supernovae. The idea here is that as you increase your sample size, you do tend to revert to the mean. You get a better estimate of the mean in luminosities of these type 1a supernovae. Now, the converse means that if you don't have a large sample size, you're also susceptible to kind of more fluctuations due to low number statistics. So as we show here in these kind of larger circles, past studies don't necessarily include the full sample size or data sets. So that's something we sought to address in our study. So we found that when we include all the data, all the type 1a supernovae, all the TRGB measurements in the literature, both HST and JWST, gives us 35 type 1a supernovae calibrated with TRGB. We do find an H naught of roughly 72.1 kilometers per second per megaparsec. But a key thing here is that we can also, with this full data set, and also kind of trace back and reproduce lower measures in the literature and explain that with subsample selection. So what we're showing here in the bottom here is a histogram of the H naught values using the same values I just showed in the last plot. And we can compare, what happens if you choose a subset of these type 1a supernovae. So we can compare to the results of another major group who also did a JWST measurement of the Hubble constant, so CCHP. If we use the full kind of type 1a supernova data set, we have this kind of distribution. We have this mean shown here with the dashed black line. If we take the 24 type 1a supernovae used by the CCHP team, that's shown here in pink, that does yield a subsample selection that yields a kind of H naught, a mean H naught a little lower than what if you had used the full data sets. That's entirely expected due to this selection of type 1a supernovae. Conversely, that also means that if you had selected the type 1a supernova not included in that sample set, so the one shown here in brick red, you would get a higher H naught. And the idea here is, of course, if you then combine them, use the full sample set, you would certainly get something in between. And so this is something we can trace back and kind of explain what happens when you use the full data set, what happens if you use a subsample, and how that affects your Hubble constant measurement. So I think kind of the main takeaway from this study is that now that we have 35 type 1a supernovae to work with for TRGB measurements, and all this data is now publicly available. There's no reason not to use the full data set moving forward for these measurements. So we kind of start wrapping things up for the TRGB side. Again, there's many, many different measurements of the Hubble constant using TRGB. Here on the right is a compilation plot of H naught values from the distance network paper from Stefano Casertano's paper, 2025. And many of these measurements you are from different teams, either even different, candles, type 1a supernovae versus surface brightness fluctuations. I want to emphasize too that, many times there's a lot of attention given to just a few groups, one or two groups in these, TRGB or H naught, local H naught measurements in the literature. But really, as shown here, and also what I presented just a little bit ago, is that there's a lot of independent teams, a lot of people working on measuring TRGB-based Hubble constants that are doing really great work too, and are contributing to this investigation. So, as I mentioned before, there are differences definitely in these Hubble constant values. Now, sometimes some teams get a lower Hubble constant value that might be a little closer or sit in between the early and late universe Hubble constants. Some teams get a little higher Hubble constant values. There's no surprise. So, a lot of these differences are documented and traced for us. So, there's a lot of good descriptions. And for instance, Deep Anand's paper, Dan Skolnick, Wendy Friedman paper, Stefano's paper, some of my paper, that really traces these differences and kind of elucidates why we see these differences in the Hubble constant. Now, I did also want to note that there is also a recent kind of community effort that we've kind of been pushing. I'm sure many of you guys are kind of aware of Cosmoverse, but for those who aren't, Cosmoverse is a research network, a cost action that's led by Eleonora De Valentino and Jackson. The goal here is to investigate these observational tensions in cosmology, and I think Cosmos has been very excellent in kind of connecting the community through conferences, workshops, seminars, and other collaborative events. I believe a lot of the organizers for this conference is very involved with Cosmoverse. And so recently, as part of Cosmoverse, we did launch a data challenge. And so, as I mentioned before, there are these variations that we observe in the TRGB that can arise due to intrinsic variations, due to, for instance, we see in this contrast ratio, which the CATS team observed. There's also different measurement effects. So, as I emphasized before, you make these different measurement choices when you measure the TRGB. One such is the smoothing, for instance, as I showed here before. The smoothing can also kind of shift your TRGB measurements a little bit. And the question here is this, how do these measurement choices, how do these variations then impact the Hubble constant determinations? Well, a lot of that is investigated in the literature, such as the CATS team from Deep Anand's paper, for instance. I think it's very also important to really enable the community to explore this as well. And so what we did was we publicly released data that can be used to measure the Hubble constant, TRGB data, as well as algorithms that you can use to measure the TRGB with. These are public, these are available for the community to use. There's also a kind of introductory or educational resources in these materials so that anyone, if you're not, don't have a background in observational astronomy, even that you would be able to read, kind of follow through the notebooks, read the kind of the descriptions and measure the Hubble constant yourself. We actually held a Cosmoverse school in Bulgaria recently at the end of May. That went, I would say, pretty successfully, where he taught participants essentially how to work with the data, so the photometry, how to apply these measurement algorithms and measure these TRGB measurement algorithms using the Sybil filter approach that I described before. Also how to, apply type 1a supernova measurements to measure the Hubble constant with. And so essentially, basically giving the participants all the tools that they need to measure the Hubble constant using this publicly available set of data and algorithms. So again, this is also that wouldn't have been done, wouldn't have been possible without all the lectures. So there is UK Murakami, Louise Berval, Kayla Owens, Teresa as well as organizers involving Eleanor and Jackson and all the local organizers as well. And so right now, the data challenge is live and the deadline is upcoming. So we have released all of the materials. They're public at this GitHub repository listed here. The deadline to submit results is coming up pretty soon in about a month, so on August 15th. And again, anyone in the world can participate, go through materials, learn how to measure the Hubble constants, and submit your own value of the Hubble constant. So if you have any questions, feel free to reach out to me, Eleanor, or Jackson if you have any questions. So now I wanted to move on to the second part of the talk. This will be a little shorter than the TRGB section. Involves the JAGB, or the J region asymptotic giant branch. Now the JAGB refers to kind of this clump or this overdensity of stars shown here in a near-infrared color magnitude diagram. And it's been proposed that some sort of kind of mean or median or mode magnitude of the stars in this J region clump can be used as a standard candle. Now, this idea was first proposed in the 1980s. So, Richer was one of the main pioneers of this idea, using these carbon stars that live inside this J region as these standard candles. This was later kind of revived in the 2020s by the Rapoche, Medor, and Friedman papers. Also, kind of in anticipation of using this new independent standard candle to test, the Hubble tension and also really take advantage of JWST and the near-infrared capabilities of JWST, since this candle is really useful and bright in the near-infrared filters, such as the J and H bands. Now, the argument for why we can use this JGB or these carbon stars as a standard candle lies in the expectation that these stars has to have a relatively narrow mass range in order for a star to become a carbon star in the first place. So if the star is too massive, bottom burning will occur, and carbon will be burned before it can reach the surface of the star. And if there's not enough mass, the third dredge-up events are too insufficient to bring enough carbon to the surface of the star. So essentially, the idea is that your star, as it evolves, it has to have a mass that's just right in order for it to be a carbon star, live in this J region, and then that constrained mass range then translates into a constrained luminosity range. Now, I will say that that is a very simplified picture. There's a lot of other considerations to that we do see empirically, and I'll talk about that more later on. So again, this J region was kind of named. It's an alphabetical naming. So there's a paper, Nikolaev and Weinberg, who kind of looked at two mass data and constructed a color magnitude diagram. And they noticed these different features on a color magnitude diagram. And it happened that this J region clump was just assigned this J letter. Now, this was then taken advantage of in the Medor papers and the Rapoche papers. They recognized that there's a lot of advantages observationally to the JGB, and particularly when it's applied to measuring the Hubble constant in the current landscape. So the JHB only requires a single epoch to observe. So one set of observations to construct this color magnitude diagram. That's a constrained comparison to Cepheids, for instance, which require about a dozen to constrain their periods and amplitudes. There's also potential for the JHB to reach further than TRGB and Cepheids. Now that's because as you go to further distances, the amplitudes of Cepheids get smaller. And that also means that as they get smaller, it becomes harder and harder to differentiate Cepheids or identify Cepheids and distinguish Cepheids from other stars when the photometric uncertainties are large. And for the TRGB is much fainter than Cepheids, and the JGB. So essentially, the potential here is that essentially, where the TRGB can reach about maybe 30 megaparsecs, the JGB can reach maybe 40 or 50 megaparsecs just because of its brightness. So the goal here is that if we can reach further with the JGB, We can really then start measuring H naught using galaxies not reached with Cepheids before. Also expand the Type 1a supernova calibration sets and really test the distance ladder in ways that we haven't been able to test it before with Cepheids and TRGB. So that kind of what also kind of motivates a lot of the recent work and really trying to investigate the systematics of this method, and also seeing essentially what Hubble constant arises when you apply this method. So I wanted to very briefly touch upon some known challenges for the JGB, and this is to prime you first before I go into a review of some recent results. The JGB luminosity function. So when we take that J region and construct the histogram of brightnesses, it is irregular. And that also means that sometimes it's symmetric, sometimes it's tilted and asymmetric. That does cause variations, variations depending on which statistic you use to measure, which measurement approach you apply to measure the JGB. There's also field-to-field variation, so similar to what the cats found in their work for the TRGB. The JHB isn't always consistent depending on which field you look, even in the same galaxy. So these are some variations that kind of currently limits the applications of the JGB. And I wanted to, touch upon this very quickly. I'll revisit this later on just to kind of prime you for what's to come and when you interpret the H-naught measurements that I'll be talking about. So very briefly, I wanted to just describe how the JGB is measured. What's first typically done is you take your luminosity or your color magnitude diagram shown here on the right, and you construct a box around this J region clump as shown here. That's essentially just a set of color cuts and magnitude cuts, these horizontal and vertical cuts. And the idea here is that you select them to kind of differentiate them from these other types of stars, such as the oxygen-rich AGB stars on the left, these kind of extreme, very dusty carbon stars on the right-hand side right here. But kind of something to keep in mind is that even though conceptually the selection process is very simple, it's not necessarily very robust because as you can imagine, there's, might be a little leeway in where you construct these cuts. If you make this bluer cut a little to the left or to the right, that might include some contamination. Certainly between these boundaries, due to photometric errors, that can also lead to some other stars bleeding in. And so that's something that to be aware of. Now, when we measure the JGB, in contrast to TRGB, which are in the halos, we do have to go a little further near the disk. We typically look at the outer disk, and that's because that's where these younger stars, these carbon stars, kind of live relative to TRGB, for instance. But when we go closer to the disk of these galaxies, again, the density of the stars increase. And so we go, there's a similar problem compared to Cepheids, for instance, where when the stellar density is very high and you try to measure the brightnesses of these stars with photometry, you can get contaminating light from nearby stars that kind of bias your measurements of the brightness of your star in the brightward direction. And so there's different ways that people kind of try to mitigate this. Some people just try to select a region that's further, outer enough from the disk. You can also apply artificial star tests. So essentially you can put in a fake star and you're using your, photometry software, you have with the known brightness, recover it, and then kind of measure the difference between the inserted star, the fake star, the recovered star to measure the difference between those two magnitudes would then give you the crowding bias. And so what here is just kind of a visual example of what you can do for the JGB. Something what we did in one of the papers that I published was essentially you can construct a grid, kind of throw down these artificial stars in different regions of the galaxy, and then measure the crowding bias in certain regions of the galaxy, and apply that to your photometry to correct for this bias. Now, there's different methods also to measure the JGB kind of reference magnitude, and this varies in the literature. So for instance, you can take the mode of a smooth luminosity function. You can take the simple mean or median. You can fit a model, for instance. This varies. There's no consensus in the literature. Now, the one kind of slight issue is that when you have irregular luminosity functions, these different measurements can change. They can differ. And that can also, for very, asymmetric luminosity functions, cause differences almost 2/10 of a magnitude. And so the reason for this kind of spread, why you get different JHB values due to different methods, is because there's this non-uniform asymmetry in the J region luminosity function. And this is what causes these differences between these measurement methods. So the idea here is that if you have a luminosity function, again, your histogram of the brightnesses of these JGB carbon stars, if that's symmetric, then your mean will agree very well with your median and your mode. If it's asymmetric, they're going to differ. And that means your JGB measurement is going to differ depending on which statistic you adopt. This is something that we investigated with JWST data. We also did find a similar effect in the ground-based data when we looked at the large and small Magellanic Clouds. And so for the interest of time, I won't go into this too much, but if you have any questions, feel free to ask later. So the idea here is that one of the limiting systematics for the JGB is due to this irregularity in the luminosity function. So again, this asymmetry drives this methodological differences. And essentially, because these JHB values can differ so much depending on what statistic you use, how much it differs depends galaxy to galaxy. That does also can affect your distance measurements and also Hubble constant measurements a lot. So in that in mind, I wanted to then briefly review some of the recent JGB H0 results recently in the literature. So the CCHP team also had their own program to measure the JGB using the James Webb Space Telescope. They did a lot of really great work to kind of refine the JHB method. And this is presented in a lot of papers in the 2020s, shown here. Their major result was presented in two papers from Wendy Friedman and Abby Lee. On the right here, kind of the footprints of their observations, their JWST observations for the data they use for this program. Kind of to cut to the main idea here is that they applied and developed their own spatial selection criteria. And so how they select their galaxies is that instead of applying artificial star tests, they measure the JGB as a function of distance from the galaxy, from the center of the galaxy. And they observed that sometimes, there's a lot of variation as you go closer to the center of the galaxy. As you go further, the JGB kind of levels out. That's what they find in most galaxies, not all the galaxies. So they select their stars based on where this JGB starts to plateau. So they keep the galaxies where they see this plateau, make their measurements where it plateaus. But then in any galaxies where it doesn't plateau, they throw away in their data sets. And so they attempted to measure the JGB in 10 galaxies. They excluded 3 galaxies because their spatial selection tests didn't converge. And they do get a Hubble constant value that's on the lower side, around 67.8 kilometers per second per megaparsec. And it's consistent with the CCHP's own TRGB measurements, as well as very consistent with the early universe measurement of the Hubble constant. Now, the SHOES team also did measure a value of the Hubble constant using the JGB method. So here we're showing the footprints for the data that we use for our measurements. Again, in this selection, we did develop our artificial star test pipeline to explicitly correct for the crowning bias. So that's in comparison, for instance, in that radial test that the CCHP team did use in their measurements. Because we did see these variations that I mentioned before, in this measurement of the Hubble constant, we also adopted a lot of what we call measurement variants. And so a total of 25 different combinations of how to measure the JGB. So you have 5 different color ranges in that selection, so that selection box that I showed before, as well as 5 different statistics. So median, mean, the mode with 2 different strengths of smoothing, as well as the model fit. So the idea here is that because we see this variation in this asymmetry in the luminosity function, we want to really explore how does this choice and measurement method in measurement parameters then change your JAGB measurements, JAGB distances, and ultimately the spread in the Hubble constant. Along the way, we did also see evidence of intrinsic variations in the JAGB. So similar to the CATS observation of the TRGB, one test that we did was we had looked at two fields in the same galaxy on opposite sides of the galaxy. The idea here is that if you have the same standard candle measured in these two fields, the idea is that they should agree very well because the distance to your galaxy is fixed, right? And if your candle is properly standardized, the magnitude should be the same. We conducted this test. We measured the JGB in this east field here and the west field right here. On this plot here, we're essentially showing just the differences in the JGB between those two fields. On the expectation here is that, of course, if they were very well standardized, that this method used in the literature, very well standardized, the differences would be mostly consistent with zero. But we see as we looked at all our measurement variants, that not all the measurement variants are quite consistent with zero. So we think that that signifies that there's some still additional standardization that needs to be baked in. Um, we did find in this first iteration broad agreements between the JGB as well as Cepheids, TRGB, and Meyer distances to the same galaxies that we measured in this data set, but there is this methodological variation that I described before that arises due to the unequal asymmetry of the J-region luminosity function. This spans about 2/10 of the magnitude. So in this approach, in this measurement of the Hubble constant, we decided to kind of incorporate that spread into the error budget. We do find a Hubble constant of roughly 74.7, but with a large uncertainty. We did later expand in another iteration the sample set with new data. And again, the goal here was to increase the sample size, increase the statistical leverage of our Hubble constant measurements and comparisons with Cepheids. We do find broad agreement again with Cepheids and TRGB. We do still see this methodological issue that really limits the precision of the H0 value. So with this expanded set, we do have 15 galaxies hosting 18 Type 1a supernovae. Good agreement with Cepheids, also a Hubble constant value of 73.7, but still with a relatively large uncertainty. I think in this iteration of measurement of the Hubble constant, it is still in very a good agreement with the HSD Cepheid distance. Now you might be wondering, why are these two Hubble constant measurements with the JGB so different? And we can trace this back to the same concept as I applied with the TRGB, to subsample selection. So this is a similar histogram to what I showed before for the TRGB. You can see that if we do look at the full sample size, there is this distribution that spans, low H0, high H0s. If you do select a subsample, for instance, from what CCHP used, you do get a lower H0. If you look at the Type 1a supernovae not included in their sample, you get a higher H0. So if you include the full sample, you'd expect to get something a little smaller. And so I think, again, since a lot of this data is public moving forward, it's encouraged to use the full data sets. But of course, with JGB, because there is not so many observations compared to Cepheids or TRGB, I think this fluctuation is definitely expected. So to kind of wrap that up, the JGB has a lot of good potential, can reach pretty far, 40 to 50 megaparsecs, single epoch. It does agree with Cepheids and TRGB at the moment with the limited sample set that we have, but there is still kind of this limitation, the systematics, where there's irregular luminosity function, these intrinsic variations, field to field, that are not fully accounted for. And of course, there's no yet standardization kind of analogous to what CATS did. So I think it's very promising, competitive, needs more work, but not yet mature at the 1% level. And so I wanted to now wrap up with a little bit of mention of a recent efforts. And I believe this will be talked about later in this conference as well. Distance network. So a group of Hubble constant H0 measurement experts, 36 in total, kind of gathered at this at the International Space Institute in Bern to kind of talk about the Hubble, Hubble constant measurements of the Hubble constant, agree and disagree on different methods, and kind of combine and compare these methods. At the moment, in their work, and our work that's presented in Stefano Casertano's paper in 2025, we do find that there's good agreement between these standard candles, such as JGB, TRGB, Cepheids, but also when you look at, all the data, your Hubble constant measurements isn't entirely, it doesn't change significantly depending on if you, for instance, use JGB versus TRGB versus Cepheids. And again, this is using the entire data set. So I encourage you to take a look at that paper. And I believe, yes, that'll be talked about more later in this conference. We can also look at, what are direct comparisons between these all the JWST, HST measurements of different distances to galaxies using different standard candles, Cepheids, TRGB, JGB, and Myrons. This was in Adams Rees's paper back in 2024. You can do different permutations, compare the differences as shown here between the distances to many galaxies. At the moment, we do find good agreements between all these existing data sets, and so I think the TRGB and JGB has really shown that at the moment they're consistent with the Cepheid-based distances, HST and both JWST, to many galaxies used to measure the Hubble constant. So at the moment, using the full data set, the TRGB and JGB does not reveal a significant systematic in the Cepheids that would be able to resolve the Hubble tension. So to kind of wrap up, when I talked about the TRGB, I did present many H-naught measurements used in the literature. Something I do want to emphasize here is that, again, I realize there's maybe a lot of attention given to a few teams for these TRGB H-naught measurements, but also want to recognize that there's a lot of different, efforts, such as from EDD, CATS, Dawan, Suhail Dawan, TRGB SBF from Blakesley, for instance, that use different methods, different approaches, sometimes even different, candles in the case of Type 1a super versus Type 1a supernovae versus SBF. And so there's a whole landscape of TRGB-based measurement algorithms out there. Now, again, another thing to emphasize for TRGB is that once we include a full data set with HST and Cepheids, we do get, we can explain differences in, in the literature, TRGB-based H-naughts in the literature. A lot of that's dominated by subsample selection, among others. Use the full sample, we do find H-naught and what's kind of agreed upon between a lot of other literature values such as EDD, CATS, TRGB, SBF is a relatively higher H-naught that's consistent with Cepheids. The JGB is a relatively newer standard candle based on carbon stars, can reach about 40 to 50 megaparsecs in kind of another independent check on Cepheids and TRGB, for instance. There's a wide range of JGB H-naught at the moment. As I mentioned, there are some limitations. There are systematics, luminosity function shape, subsample selection, also these field-to-field variations. So it's promising. We can measure Hubble constant with it. Caveat is large uncertainties. But again, just to be wary of when you interpret these Hubble constant results with the JGB. Again, these differences, even for JGB and TRGB and JGB and the H-naught values, they're all documented. They're all known. And they can be traced for. So there's no mystery why there is a lot of this variation in the literature. And of course, I do want to emphasize too is that I think there's a lot of effort now to make these measurements and these data sets very public and kind of involve the community with. So there's this distance network effort that I mentioned. You can read more about that in Stefano Casertano's paper. But again, there's also this data challenge, this Cosmoverse data challenge that we recently released. And again, this data challenge is the goal is to enable anyone in this room, anyone in the world to provide the educational materials and the notebooks and the data so that you can learn how to measure the Hubble constant, work with the data set, and then kind of play around with these parameters and then see for yourself, how can you reproduce these different values in the literature? How do these variations and measurement choices then also impact the Hubble constant measurements you make, and also you see in the literature. Now, of course, this is outside the scope of this talk, but I will also note that, of course, this new instrumentation, so JWST has already contributed to this investigation a lot. Launch of Roman will also provide a lot of data that will help really improve the characterizations and refinements of the TRGB and JHB as well. So with that, I wanted to wrap up. I'd like to thank you for your attention, and I'd be happy to take any questions.
Thank you, Sean. Also, impressive performance from Sean at now almost 2 a.m. for him. But thank you for the very exhaustive review. It's coffee break time, but we'll take a couple of questions that are urgent, and then we can iterate with Sean also online later on. Any quick questions that people have in mind? All right, just ask one, and then we go for coffee break. I'm just curious to know, when are you going to get to 1% precision with TRGB or JAGB, you think?
Yeah, so I would say I'm hopeful with the launch of Roman, because after launch of Roman, so I mean, very optimistically, maybe a few years. The reasoning for that is because, as I mentioned before, what, like, for instance, Katz found that there are still some variations in, the TRGB as well. Now they were able to kind of try to standardize for that with the contrast ratio, but what would really benefit for kind of refining the TRGB method is also kind of getting more data, field to field data in the same galaxy. And with a very, very wide field of view with Roman, for instance, we can then get the data to really test and refine the TRGB even more, to really beat down those systematics, and then hopefully reach maybe a 1% precision as well. Um, and so, yeah, so that's, fingers crossed. Roman's scheduled to launch very soon, so hopefully that will go smoothly.
Okay, great. That is very exciting. Thank you again. And now you can go to sleep now.
Okay, thank you. Yeah, thanks again for the flexibility and with giving this talk virtually.
See you
And
soon, and everything is good on your side.
okay, yeah, thank you so much.
Bye bye.
All right, bye.